All right, let's dive into one of the weirdest, most powerful forces in our solar system. We're going to talk about how something as seemingly gentle as sunlight can actually steer millions of tons of rock through the emptiness of space.
It really sounds like a riddle, doesn't it? I mean, can sunlight, something we think of as totally weightless, actually move a mountain? Here on Earth, no way, of course not. But out there, in the vacuum of space, well, the rules are completely different.
And the answer is a huge, mind-blowing yes. It's a process that's so incredibly slow it's almost impossible to see. But you give it a few million years, and the gentle push from sunlight doesn't just nudge asteroids, it literally redirects them, sculpting the very architecture of our solar system.
So how on earth does that even work? Let's break down the physics behind what really feels like an impossible push.
You know, I love this quote because it just nails how bizarre this whole idea is. In our everyday world, light doesn't push stuff around. But the physics get really weird when you take away friction and just add a few million years to the clock.
So here's the secret. In space, photons from the sun don't just carry light, they carry momentum. They give a tiny, tiny push. But what's even more important is that they deliver heat. And it's how an asteroid gets rid of that heat that becomes the real engine for all this motion.
Okay, let's get into the nitty-gritty of how this works. The phenomenon that makes this all happen is called the Yarkovsky Effect. And a great way to think of it is like a microscopic thruster, just firing away, continuously, for ages.
So that's the official definition, the Yarkovsky Effect. Now that might sound a little dense, but the words you want to hang on to are thermal recoil and uneven heating. See, it's not the sunlight hitting the asteroid that does most of the work, it's how the asteroid cools down afterwards.
This breaks it down perfectly. So, first, imagine the sun just baking one side of the asteroid, its day side. But the asteroid is spinning, right? So that hot surface rotates away from the sun, becoming the evening side. And as that hot rock cools, it radiates its heat out into space as infrared light. And that radiation, that escaping heat, actually has momentum, and it gives the asteroid a tiny continuous push in the opposite direction.
And this is the perfect way to picture it. Every single time the asteroid spins, this little thermal thruster fires. Now one push is, well, it's basically nothing. But what happens after a billion pushes? Or a trillion? That's when things start to get interesting.
So let's look at how these tiny, tiny pushes actually add up. This is where you have to start thinking in cosmic time, where these microscopic thrusts can cause solar system-wide migrations.
This effect is strongest on the smaller guys. We're talking asteroids under about 30 to 40 kilometers across. Bigger asteroids just have too much mass, too much inertia for this tiny force to do much. But for the smaller ones, oh, it is an absolute game changer.
The real power here is just accumulation over massive amounts of time. Within just a few decades, our instruments can actually measure the orbital drift. Fast forward millions of years, and that same gentle push acts like a cosmic slingshot, flinging asteroids from the main belt all the way into Earth's neighborhood. And over billions of years, this effect has helped reshape entire families of asteroids.
Now, this isn't just some cool theoretical trivia. Understanding this effect is absolutely critical, especially when an asteroid's path might, cross our own. And that brings us to a very special asteroid named Bennu.
And this is exactly why this matters so much. It's all about planetary defense. If we want to know if an asteroid is going to be a threat hundreds of years from now, we have to get its path exactly right. And if you ignore the Yarkovsky effect in your calculations, your prediction is going to be wrong. Factoring in this tiny thermal push can be the difference between we're safe and uh-oh.
This is why missions like OSIRIS-REx are so incredibly important. By getting right up close to Bennu, scientists could precisely measure its size, its shape, its spin, even what its surface is like. All of those little details change how it heats up and cools down, which lets us build way more accurate models of where it's going to be in the future.
But hold on, because changing an asteroid's orbit isn't the only trick sunlight has up its sleeve. The Yarkovsky effect actually has a rotational cousin that's just as powerful. It's called the Yorp effect.
This chart lays out the difference perfectly. So while Yarkovsky gives an asteroid a straight-line push that changes its orbit, Yorp gives it a twisting force, a torque, that changes its spin. It's caused by the same basic idea of uneven heating. But because asteroids are all lumpy and weirdly shaped, the heat radiates off unevenly, causing it to spin faster or slower over time.
And the consequences of this Yorp effect can be super dramatic. Over long periods, it can make an asteroid spin faster and faster, or slow it to a crawl, or even make it tumble through space.
And in the most extreme cases, it can spin an asteroid so fast that it literally flies apart, creating whole new pairs or families of asteroids.
So when we put all this together, what does it really mean? It means sunlight isn't just some passive thing that gives us light and warmth. It's a relentless, silent cosmic sculptor constantly reshaping our solar system.
That's the big takeaway. Together, these two effects prove that sunlight is an active force. It's always at work, tweaking orbits, changing spins, and reshaping all the small objects traveling between the planets. It's a quiet, invisible process, but it is always, always happening.
This quote just says it all, doesn't it? The force is tiny, almost non-existent, but its persistence is absolute. Over the immense history of our solar system, that gentle light becomes one of its most powerful and transformative forces. And it kind of leaves you with this one last, fascinating question. If something as familiar as sunlight can have such a profound and hidden influence, what other quiet forces are out there, silently shaping our universe right now?